Okay, today we will continue on talking about salt solution. I hope you have studied your previous lecture because all of these lectures depend on each other. So please do not postpone studying the lecture before. If you have not studied that lecture, study it before you listen to this lecture. Speciation of the salt solution. A mass balance equation for the total concentration of a metal, Mt, with N plus valence in the solution phase can be written as Mt, T for total, N plus, which is any cation of the valence N plus, equals Mn plus, which is the free ion, plus the Ml, where Mn plus is the concentration of the free hydrated metal ion species. You remember we have said that any of these cations will be present in two different forms, the free hydrated metal ion itself and the concentration of metal ion associated with the remaining metal ligand complexes. So all the other complexes, we call them ML, which means the metal complex with ligands. The ligands in the metal ligand complexes could be inorganic anions or humic substances such as humic and fulvic acid. So they can be inorganic or organic ligands. Similar mass balance equations can be written for the total concentration of each metal and ligand in the salt solution. So think of this general equation carefully. So the total concentration of any metal ion, remember we get this one from the laboratory analysis. When you run any analysis for any metals, you get the total concentration. This total concentration should equal the free hydrated metal ion species plus all the complexes of the metal with the ligands that are available. Now we talk about two different equilibrium constants that we can deal with in soil chemistry: the conditional and thermodynamic equilibrium constants. The formation of each metal ligand complex in the salt solution can be described using the complexation reaction and a conditional stability or conditional equilibrium constant K conditional. This is to indicate it's the conditional, not the thermodynamic. We will explain the two of them and the difference. Conditional stability constants vary with the composition and total electrolyte concentration of the salt solution. So that's why it's called conditional. It depends on the conditions and the composition of the salt solution that they're in. So, and the total electrolyte concentration, we will talk about that later. How do we measure that? The total number and amounts of all the electrons, sorry, of all the ions that are in solution. These are all affecting the conditional stability constant. Conditional stability constants for inorganic complexes, however, can be related to thermodynamic stability or thermodynamic equilibrium constant, which we call K0. K0, or this thermodynamic stability constant or equilibrium constant, are independent of chemical composition of the salt solution at a particular temperature and pressure. So the only thing we have to tell and give as conditions for the thermodynamic equilibrium constant is the temperature and pressure. And most of the times, these are determined at what we call room temperature, which is 25 Celsius, and 1 atmospheric pressure, which is the normal pressure found in any laboratory. If we take a simple reaction, A of A plus B of B. Of course, this is reversal conditions. C of C plus D of D. So the A and B are the reagents that are reacting, the reactants, and C and D are the products. And remember, we have already called this small a, small b, small c, small d, the stoichiometric constants. Stoichiometric constant to balance the equation for atoms and also charges. A thermodynamic equilibrium constant K0 can be written K0 C to the C multiplied by D to the D over A to the A, capital B to the B. So this is the equilibrium constant that you have studied in chemistry. This is the one that's not affected by the combustion. A conditional equilibrium constant, K conditional, can be written as K conditional. The only difference, if you can see here, we have what we call parentheses. These are parentheses, and these are brackets. Parentheses will indicate the activity of C, the activity of D, the activity of A, the activity of B, while these brackets indicate the concentration, the actual concentration we measure of C, D, and A and B. The small superscript letters refer, this one we talk about, refer to the stoichiometric coefficients, and A, B, C, and D are the chemical species, reactants, and products. We will take as an example of the speciation of a salt solution. Remember, the purpose, as we started from the beginning, is how to find all the different species of any of the elements in salt solution. The process is called speciation, finding the different species. The process is speciation. To illustrate how mass balance equations and conditional equilibrium constants can be used to speciate, this is the verb, speciate, speciation, to find the different species. A metal ion in a salt solution, we will calculate the concentration of the different calcium species present in a typical salt solution from a basic soil. We take a basic soil, alkaline soil, because calcium will be prevalent. It will be found in good amounts. If we take an acidic soil, you don't expect very much calcium. Assume that the pH, these are assumptions as an example to study it so that you can apply this to any real situation, but we always give an example assumption so that we can see how we do the process. Assume that the pH of a salt solution is 7.9, which is alkaline basic, and the total concentration of calcium, Ca total, which we get from the analysis in the laboratory, is 3.715 times 10 to the minus 3 mole per liter. For simplicity's sake, so that to make the example easy to handle, easy to follow, so we simplify things. It's not realistic 100%, but it's the same. Whether we add, as you will see, we can add more ligands, but the same process, but we simplify it, take smaller number, so we can deal with them much easier and see how we do the process. So for simplicity's sake, and realizing that other complexes occur, so this will be not the only ones, but we are going to simplify and assume that's what we have. Let's assume that calcium exists only as free hydrated calcium. That's the free ion, which is hydrated also, as you remember, we have said earlier, because it is in solution, it's surrounded by water, so it will be hydrated, surrounded by water of hydration. And as complexes, with the inorganic ligands, carbonate, sulfate, and chloride. So we're assuming we have only carbonate, sulfate, and chloride. So we are going to apply the mass balance equation. The calcium total, T always for total. Remember, we don't put any charge on it because that it includes all the species. Ca total can be expressed as the sum of free and complex forms as, so we write it as Ca total. Remember, we get this one from the laboratory analysis, equals calcium, which is the free ion, plus calcium ion pair with carbonate. Carbonate, remember, CO3, it carries 2 negative charges with 2 positive charges, so it has 0 charge. So that is the ion pair, if you remember. And we have CaHCO3 plus the bicarbonate HCO3 minus, it has 1 negative sign. Calcium has 2 positive signs, so the complex will have 1 positive sign or charge. Then calcium sulfate, just like the carbonate, sulfate SO4 2 minus, it has 2 negative charges. With calcium, it forms an ion pair of 0 charge, plus CaCl plus calcium divalent 2 plus, chloride 1 negative, so the complex will have 1 positive charge. Now the question, if you look here, we talked about carbonate, sulfate, chloride. Where did we get the bicarbonate from? Did any one of you think about looking at these do not contain carbonate, and here we automatically wrote a complex with the bicarbonate. The bicarbonate comes from the hydrolysis of the carbonate. Hydrolysis, when it's in aqueous medium, it will immediately take a hydrogen from water, so it will become HCO3 minus, it carries 2 negative charges as an ion. If it takes hydrogen, then it becomes HCO3 minus. And that's why here we have calcium divalent, bicarbonate, 1 valence, negative valence. So CaHCO3 will have 1 positive charge. So that's where the bicarbonate, anytime you are given carbonate, even if you are not told about the bicarbonate, you have always to add it, because carbonate will always hydrolyze in water to produce bicarbonate. You cannot have carbonate without having bicarbonate. So this is automatic. They don't have to tell us here there will be bicarbonate. We know they should be bicarbonate, so we add it. Where brackets indicate species concentrations in mole per liter. Remember, in the conditional equilibrium constant, we said the brackets indicates concentration. So these are concentrations in mole per liter. We continue on. Each of the above complexes can be described by a conditional stability constant. Remember, each of these formed through a reaction, which is the formation of the complex. So in this particular case, CaCO3 0, this ion pair is the complex that formed. Formed from what? From calcium plus carbonate. So you say on the left, we would have calcium plus carbonate to give us CaCO3, this ion pair. So to write the K conditional for that, this will be this way. This is the product over the multiplication of the reactants. And this is K conditional because we are using the concentration brackets. The same thing we do with the rest of them. K2 is for the bicarbonate formation. Remember, calcium plus bicarbonate will give you calcium bicarbonate complex, and you write K2 for that, and so on for the rest of them. This one for the sulfate complex, this is for the chloride complex, as we have seen on the previous slide with the mass balance equation. Since the above equations have calcium as a common term. Remember, all of them contain calcium, all of these. So this is a common term, the concentration of calcium in all of them and each of the inorganic ligands. So we can rewrite in a different way, simplify and make it written in a different way. The Ca total can be expressed as the sum of free and complex forms as Ca total equals Ca2 plus the common term, we got it out. We put parentheses of this is multiplied by all these. Remember, if you multiply this, if you open these brackets, calcium will be multiplied this, so this will be here Ca2 plus, and then calcium multiplied by this will be this, and calcium multiplied by this will give us this, and so on. So Ca total will be Ca2 plus. Of course, you go back to the equations we have seen on the previous slide, and you can find why we have this one written this way. So the CaCO3, you will find that it's written as K1 conditional times carbonate, K2 conditional multiplied by HCO3. This is from the previous simple math from the previous slide, plus K3 conditional with the sulfate, plus K4 conditional times the chloride. Try to do it from the previous equations that we saw on the previous slide. Look at them and find the value of each one of those so you can see where we obtained these. Simple mathematics, nothing hard about it. Continue on. The mass balance equations can be expressed for total metal and ligand concentrations MT, N plus, and L for ligand, T and N minus, which each one of them has a different valence, respectively for each metal and ligand species. So we took calcium as an example, but we can do this same thing for all the metals or the cations that are in the salt solution we have, and all the ligands, whether organic and inorganic, that we have in that salt solution. The mass balance expressions are transformed into coupled algebraic equations with the free ion concentration as unknowns by substitution for the complex concentration. This is kind of a little difficult language for you, but what it means in simple ways, all these mass balance equations that we have written, these expressions, these equations, just like the one we have seen for calcium, they are transformed into coupled algebraic equations with the free ion concentration as unknowns by substitution for the complex concentrations. So this is done first on a mathematical basis, and then it's very difficult to solve so many of these equations at the same time. They used to do it by hand, simple calculations by calculators, sit down for days and days to do this. But nowadays, we have computer equilibrium models that you put in this data in these models, and they will do the calculations for you in very short time, just by press a button and you get all the information, all the species. But it's for us, it's good to understand how we did it, how did we enter the data, what kind of data we needed to enter in these models so that they will give us what we need. So the thermodynamic databases contain equilibrium constant. These databases that are in these models, what do they contain? Thermodynamic databases contain equilibrium constants. These are available. They are available in chemistry books and thermodynamic books. So we just look for them and find them. For aqueous complex species, as well as other equilibrium parameters we need. The free ion concentrations obtained, so eventually we will obtain the free ion concentration of all the ions that are in our salt solution that we collected. the free ion concentrations, we obtain them from these equilibrium models obtained from the iterative approach can then be used to calculate the concentration of the metal ligand complexes. How are these built, these models? They depend on what we call iterative approach. The iterative approach, you have seen something similar in your math when you studied math. It's called by approximation. You assume a certain value at the beginning, and then you calculate. If you find it different, higher or lower than this, sorry, the ion concentration, which is the total concentration which you have, that's the real value you obtain in the laboratory. So you compare the calculation when you add them all to that value and see, is that higher or lower? And then based on that, the next time you get another assumption. And you keep on with this approximation or iterative approach until the total will give you the concentration that you have from the laboratory analysis. Then you say, my values are correct. So example, now suppose we have calcium ion concentration. We know, okay, because we obtain the free ion concentrations from these model calculations. Okay, so Ca2 plus H plus carbonate to give us the bicarbonate. K conditional for HCO3, this we can obtain from the databases we talked about. This is available in the chemistry books and in thermodynamic databases. So it is found to be 9.33 times 10 to 10 at 298, which is the Kelvin temperature of the room temperature is 25. Substituting this value into K conditional equation. So K conditional, that's the value of it, equals this over all these. Calcium, HCO3 over calcium, hydrogen, and carbonate. So, and solving for, see, remember, we obtained all the values of the individual ions. So now we have the value for this, we have the value for this, and we have the value for this. So solving for CaHCO3 plus, remember, calcium divalent, HCO3 -1. So this complex has a +1 charge. It gives CaHCO3 equals 9.33 times this. You multiply this equals this. This is over 1. So this equals this times this. 9.33 times 10 to the 10 times calcium times hydrogen times carbonate. Once the free concentration of calcium, hydrogen, and carbonate are determined, like we said, these will be determined from the iterative approach that we talked about, then the concentration of the complex CaHCO3 can be calculated from the previous equation. The calculated concentrations for the various species can be checked by inserting them into the mass balance equation and determining if the sum is equal to the known total concentration. So remember, the total concentration is the real value, the only value we know is correct and true because we obtained it from our good analysis in the laboratory. So that is value which we know it's correct. So we add all this with all the calculated concentrations of the various species, we add them all together, and they have to equal that total concentration we obtained in the laboratory. If they did not, something is wrong with our calculations. We have to repeat, we have to find where the mistakes are and redo the whole thing again. Read in your text explanation of example from table 4.3. If you look at table 4.3, there is the example given in your textbook. It will explain again what I have just discussed. And if you have any problems, you can ask through email or through any other way if you want, if you have any problem understanding some of this material. Okay, we finished this.